In this tutorial, we'll show you how easy it is to create your own human-machine interface project in the C++-based Qt development framework for your CoolMotion application. The CoolMotion installer does not include the Qt programming environment, so it must be installed separately. Let's open the first Motion project that we already saw in our previous video. Make a copy of it under a different name. Open the CM main function block. Select the Communication Interfaces menu on the right panel of the CM main. In this menu, we can assign communication interfaces to the inputs and outputs of CM main. This allows us to create a connection between two or more applications running on different computers or embedded hardware platforms. Let's see how. Click the Add button. Name your interface. Then choose a communication type from the list, whose items may differ by hardware platform. The SMEMPP communication type is a point-to-point connection via the computer's shared memory. It is a very fast connection, however the other program or HMI must be on the same device as the CoolMotion application. During compilation of the CoolMotion project, HMI skeleton projects are also generated for Qt, C# and Python environments. The SMEM communication type is also a connection via the computer's shared memory. In this case, a shared library is generated with access functions for the inputs and outputs of CM main. Using this library, multiple applications and HMIs can connect to our CoolMotion application simultaneously. The UDP interface establishes a client-server connection based on UDP IP protocol. For the CoolMotion system, the physical layer is Ethernet. If the UDP server communication type is selected, the CM application will be the server. During compilation of the CoolMotion project, HMI skeleton projects are generated as client. The UDP client setting is only used when two CoolMotion applications need to be connected to each other. In this case, one interface should be set to UDP server communication type and the other to UDP client. OPC is a standardized remote communication interface for secure and reliable data exchange in industrial environments. It is platform independent and ensures a seamless data flow between devices from different manufacturers. Now let's select the UDP server communication interface for all platforms. In the right panel, interfaces can be assigned to inputs and outputs of CM main. Now let's assign the interface to all inputs and outputs. Of course, you only need to assign an interface to the pins used in the HMI. Only one interface can be assigned to an input. If necessary, more than one interface can be assigned to an output. Save the changes and build the project. During the compilation, skeleton HMI projects have been created into a folder named Generated inside the CoolMotion project. The generated code was placed into two folders, both prefixed with INTF. One folder contains common program components, the other contains the UDP client-side source codes. Let's make a copy of these using the File Explorer program, and paste them into a new HMI directory. Now, let's look at the generated Qt projects. In the HMI Qt directory we find two Qt projects. One is the HMI base project, which has control elements for all inputs and outputs of our application. This program can even serve as a sample program for HMI development. The other is the HMI empty project, which contains an empty window. This project can be a good starting point for creating your own HMI. Let's review these two resulting projects. First, open the HMI base project with the Qt program. We can accept the default configuration settings. Let's run it. The project is being compiled, which will take some time. The main window appears with the outputs and inputs of CM main. Start the virtual machine and launch the application. Now check the operation. The enable input starts the connection to the virtual SBCMI card. The valid output indicates that it has been done. Power on the axis. Let's start the motion with the start button. The target position is set to 20 revolutions. When the axis has reached the target position, the done output will be true. In addition to the generated Qt HMI, run the integrated minimal HMI from the desktop. The minimal HMI detects the interfaced pins of the CM application and displays them in read-only mode. The application can only be controlled from the generated Qt HMI. Change the target position to 0. Start the motion by switching the start button off and then on. Observe the operation of the two HMIs together. Close all running applications. Restore the Qt Creator window from the taskbar and observe the structure of the generated HMI base project. It is a Qt widget application including a Qt Designer-based main window. Let's open the main window UI with Qt Designer. All visual components are positioned with a layout widget. The input and output panels are placed on a scrollable and splitter-equipped area, so the window and all elements can be resized at runtime. The HMI update rate is set by the spin box. The Boolean type inputs are controlled by push buttons, and the target position by a double spin box. The output values are displayed by labels. The source codes required for all visual widgets to work are located in the file's main window CPP and main window header. By modifying these files, we can create our own HMI. This modification can also be done using artificial intelligence. Now let's take a closer look at the content of the created interface project. For easier understanding, we will do this with the empty project. Open the HMI empty project with the Qt program. We can accept the default configuration settings. The empty project has exactly the same structure as the base project, except that it lacks the visual components and their codes. It is a project with an empty window. Let's review the source files. The INTF Common Library contains the source code of the UDP interface, including type declarations, UDP communication, and support for more complex data types such as arrays, plot, and 3D graphics viewer. The main Windows CPP file is the source code of HMI components. This will be discussed in more detail later. The INTF UDP interface class CPP is the source code of a UDP communication interface class through which we can access the inputs and outputs values of our application. We will look at this class in more detail later. The main CPP file contains the main function of the HMI application, including the instantiation of the main window and queue application. Now let's take a closer look at the header files belonging to the source codes. The main window H is the header file of the main window Quidget class. The private variables are as follows. The user interface pointer of the form window edited by Qt Designer. The UDP communication interface class to access the inputs and outputs values of the CoolMotion application. A timer class for the cyclical refreshing of the inputs and outputs elements of the HMI. This timer will run cyclically a private slot function called timer cycle function. The header file contains an additional Boolean variable to store the initialization status. Let's see the header file of the UDP communication interface class. This class is the interface between the CoolMotion application and the Qt HMI, allowing reading and writing the inputs and outputs. When building your own HMI, all you need to do is instantiate this class and use its public functions and variables. Let's have a look at these functions. The connected function indicates that the connection between the Qt HMI program and the CoolMotion project has been established. The inputs-outputs data valid function indicates if the values of the inputs and outputs are valid and usable. The in-out struct is a structure with elements corresponding to the inputs and outputs of the CoolMotion project. This structure is updated cyclically. The update rate of the cycle is changeable using the setUpdateRate function. Let's see the structure declaration. You can see that the names of the structure elements correspond to the CM main input and output names. When writing our HMI program code, we access the CM main ports through these variables. During the updating, the input elements are copied to the CM project's inputs. The CM project's outputs are copied to the output elements. Let's look at the main Windows CPP file. It's just a constructor, a destructor, and a cyclic function for timer of our HMI. The constructor calls the designer UI setup function, sets the timer event to the cycle function, and starts the timer with a cycle time of 10 milliseconds. In the cyclic function, you can adjust the visual control elements of the HMI. The generated program contains empty sections that the user can fill in. Their locations are indicated by comment lines. The program code written in the first two empty sections is executed when communication between the interface class and the CM project is established. The initial values of the input and output widgets can be specified here. The next empty section is placed in the part of the function that runs in each cycle. The program code that updates the values of the output widgets can be written here. We have already seen the structure of the two automatically generated projects. Now let's create our own HMI, starting from the empty project. First, let's make a copy of the empty project with a different name. We need to copy both the HMI empty directory and the HMI empty project file. Let's name them HMI First Motion. Then, open the HMI First Motion project file you just created using the Qt program. We can accept the default configuration settings. For our copy to work properly, we need to modify the source code path within the HMI First Motion project file. Open the project file. Replace the HMI empty directory path with HMI First Motion. Save it and then compile the project. Let's check if it works properly. Let's start it. Everything is fine. Our empty window has appeared. Now we can start working on placing the control elements of our own HMI. If you are not familiar with Qt, then artificial intelligence can be a great help in designing and coding your own graphical user interface. Open the main window UI file for graphical editing in Qt Designer. Let's place a group box. Next, add a push button for the enable command. The enable button should act as a toggle switch, so check the checkable property. Add a label for the valid status output pin. Similar elements are also needed for motor power control. Now we will add the components required for motion control. To indicate the done output, a green background label is displayed, which is only visible when the done output is active. To change the target position input, we'll use a double spin box. All that remains is the label needed to display the actual position. Save the project. Let's continue by code writing. We will use slot functions of Qt to operate the push buttons. Use Qt Designer, go to slot menu for this. This is an automatically generated event function that is called when the enable button is pressed. The current state of the button is provided by the value of the checked function parameter. Our task now is to transfer the changed state of the enable button to the CM main enable input within the body of this function. We can achieve this by setting the member variable enable of inout struct to the function parameter checked. Let's see. Save your changes. Now, write also the toggle event functions for the power and start buttons in a similar way. For the target position visual control, select the value changed event function of the double spin box. The value entered in the Qt double spin box is passed in the arg1 function parameter. Now we can change all the inputs of our program. All that remains is to give the visual elements of the inputs initial values so that they show the correct value when the program starts. This can be done in the cyclic function of the timer, within the first commented section. The program code written in this section is executed when communication between the interface class and the CM project is established. The initial values of the input widgets can be specified here. Let's see how. We are done with controlling the inputs. Now let's move on to the outputs. We'll display all 4 outputs of the example program using Qt labels. We will change the background color and text of these labels to reflect the current state of their corresponding outputs. This can be done in the cyclic function of the timer, within the third commented section. The code written here runs in each cycle according to the timer's timing. Let's start with the valid output. If the valid output is true, its label's background color is green, its text color is white. And its caption is valid. In the else condition, the label's background color is the default, the text color is black. And the caption is disabled. Write a similar code for the power status output as well. The small difference is the label's text. It is on in the active case, and off otherwise. Next comes the done output of the motion. The label for this output has already been created in the designer. It just needs to be shown and hidden according to the output state. For the correct initialization, we need to hide the label done in the Windows constructor. We're almost done. We just need to write the code for the actual position label. To display the output value correctly, we'll convert it to text. We are ready. Save the modifications and rebuild our Qt HMI project. Now, let's launch our Qt HMI. Let's start the virtual axis and the first motion application. Let's try it to see if everything works. We have done a great job. Thank you for your attention. For more information, visit our website at link to freemotioncontrolsoftware.com.